Hello everyone, and thank you for tuning in once again to the Group Theory Podcast. This is the show where we talk to working mathematicians about what it's like to do research for a living. My name is Logan, and today we are joined by Dr. Fridtjof Leutscher. He's a professor of applied mathematics here at the University of Ottawa. Dr. Leutscher has just under 80 publications and incredibly over 1,800 citations. I think you're the most cited mathematician on the show so far.
Oh.
I could be wrong, but I think so. And those citations are on his works in mathematical models of biological systems. I'm going to let him pronounce the university where he got his PhD from.
University of Tübingen oder Universität Tübingen.
All right. He got his PhD in the year 2000 on the subject of modeling moving polarized groups of animals and cells.
Yes.
So without further ado, thank you for joining me today.
Thank you very much for having me.
Well, it's my pleasure. So I guess we'll just jump right into this. What's your field of research, and how would you describe it to a non-math person?
Okay, so I usually say I work halfway between mathematics and biology, and that gets most people interested somehow. So in terms of the mathematical side, I do dynamical systems. Could be ordinary or partial differential equations or discrete time systems, something like that. In terms of biology, I usually do ecology. That's what I'm most interested in. So typically I'm interested in how individuals move around in space and how they interact with others, and then what that means for the population level, whether populations persist, whether they go extinct, whether they spread in space, whether they form fancy patterns. So all of those things is what I'm interested in.
Very cool. So actually, I wanted to ask you specifically about, there's a couple of your publications that have to do with both cells and groups of animals and their movement.
Yes.
So correct me if I'm wrong, but cells in the biological sense, like with a nucleus, mitochondria.
Yes.
So these groups of animals and groups of cells, they move in a similar way? Why group those together?
Yeah, I think this is one of the powers of mathematics, that you can describe abstractly particles that follow certain rules. And then the scale at which you look or the particular application doesn't matter. As long as they follow the same kind of rules, you can use the same kind of equations and study these equations. These equations are indeed in principle the same, or at least qualitatively very similar, for cancerous cells, for animals, for flocking birds, for all kinds of things. They're all, in this particular case, reaction diffusion equations, and they can describe phenomena on many different scales and levels.
That's very interesting, because you wouldn't think that, groups of animals and cells behave the same way at all at any kind of scale, but I guess, if the math works. But I wonder, could you dive a little bit deeper into that? Like, what exactly are some of the similarities in the equations that model cells versus modeling groups of animals? Like, how are we able to say that they're the same? What characteristics of cells and groups of animals make the structure work? Okay,
so if I'm modeling the movement of an organism, then I associate some things like rates or probabilities. In the simplest case, let's say I have an organism that moves just along a line or very thin corridor, just for simplicity, then that organism has a probability of moving to the left or to the right or staying. There isn't much more that it can do. And so if I write down expressions for these probabilities, then that's all that my model needs, right? And whether in the end I'm thinking of this as a small cell, a tumor cell in a brain somewhere that moves somewhere in your brain, or hopefully not in your brain, or an animal that walks along a corridor, a wolf that tries to catch its prey, or a deer that tries to get away. It's then just a matter of what is the scale, what is the length scale that you're looking at? Is it centimeters and millimeters, or is it hundreds of meters or kilometers? And the time scale. Is it on the order of, let's say, hours and days, or is it on the order of years? But the equations themselves don't really see that. The equations only see there is an organism that moves, or particle that moves one way or the other.
Very cool. So then, this is obviously a very simple case of something that can move left or right,
Yes.
and or stay where it is. So, but if, say, you were tasked with coming up with a mathematical model for, say, how a disease spreads, because I know that's something else that you are interested in, right?
A little bit.
A little bit. So how exactly would you, say, look at that problem and then boil it down to those really fundamental things like moving left, right, or staying where it is?
Mm-hmm.
How do you look at these really complicated systems that are at least complicated at face value, and then reducing them to their bare bones so you can build a mathematical model from them?
So if I may change the subject slightly, I would
Sure.
say let's go for biological invasion rather than a disease.
Sure, okay.
Because I know a little bit more about those than diseases. So what I like to start with is I like to talk to the people who actually study the organisms that I want to study. I mean, maybe I read about it in a journal. I read various ecological journals, and I hear something maybe just in the radio. So here in Ottawa, we had the emerald ash borer come through. A lot of ash trees were cut down because people were concerned that the emerald ash borer would go in there, would multiply, and then kill even more trees. And so some of these trees were cut down preemptively, so to speak. And so the stories of biological invasions are all around. And first thing is I like to either go to the literature or go to the experts and talk to them and ask them what they think is interesting and important about this. And then, of course, I have my experience for what has been important in other models. So one thing we know, for example, in the very simplest model, what's really important is how many offspring does one organism have per generation, and then where do they go? And now I have to be a little bit careful, because if I say how far do they go, then that seems very obvious. But this how far they go is typically some kind of a distribution. Some of the offspring go far, some stay close. And it turns out that the average distance that they go is not the important number that we want to know.
Really?
It's more the outliers that we need to know. And so then in the simplest case, I say, okay, can you give me those two? Can you give me characteristics for those two things? And then usually the biologists say, well, it's actually a little bit more complicated with this organism. And then I find out what these things are. And usually there is a middle ground. If I try to put everything into a model, it becomes too hard, intractable, not just mathematically, but even just to simulate or to get enough data for it. If I make it too simple, then I'm missing things, obviously. So I'm usually putting as many things in as I can, and still treat the model with the techniques that I know or that I develop. And then I hope that the answer is somewhat helpful.
Okay. So it sounds to me then like there's a lot of statistics and probability involved in the kind of work you do.
So typically I delegate the statistics to other people. Well, I don't know much about statistics. So statistics, the ecologists do, and they do much better than I do. They have their empirical observations or experiments, and they do the statistics on those. But yes, my work contains a lot of probabilities, probability distributions that go in, for example, the probability distributions of distances moved by a particular organism. That's one of the things that goes into my model. Yeah.
Very interesting. Okay, so this is probably going to be a bit of a stupid question, but I'm sure you've heard of like the hierarchy of the sciences. So like there's mathematics as the most pure, and then physics, then chemistry, and then biology, right? So my question is, in essence, why do you think that mathematics is such a powerful tool for studying something like biology, where it is this kind of anomalies pop up all over the place, and it doesn't follow these super duper strict rules. It's more of these probability distributions. Why does looking at partial differential equations or differential equations, how does that really help us?
That is a tricky question. So one thing I would say, okay, so it depends on what you do, and what levels, what tools of mathematics you use. Mathematics can be really good to test hypotheses and to tease apart different mechanisms in biology. So biologists often have ideas of many aspects of a particular system that they want to take into account, that they think are all important. But of course, in a system, it's difficult to study them separately because it's a real system out there and you can't just turn off something or turn on something. But you can do that in mathematics. If you put these hypotheses into models, you can turn a parameter on and turn it off. And then you can study what would happen if this thing wasn't there. And you can get an answer, and you can see how close that answer is to the answer that you see in the field. And if it's close, then you can think, well, maybe that process is not so important. And if it's not close, then you can think maybe that process is important and I need to look at it more. So I think that's how a lot of people use it. There is another way in which mathematics really keeps you honest, because everything that you put into an equation is based on some hypothesis, and if you can write it down, you can't be ambivalent about it. You can't be ambiguous about it. It has to be that thing or that thing or that thing. So it really keeps you honest in terms of what assumptions you make in your model and what goes in and what doesn't. It really helps clarify that thinking. Those are definitely two things that I use. People who do more statistics and more computational biology, I think have a lot of other uses for mathematics as well, because it is difficult to do experiments on large spatial scales, on very small spatial scales, easily repeatable, fast speeds. A lot of these things can be done by computers, kind of the model experiments. And for many things, we wouldn't want to do the real experiment unless we know that it would be a really, really important experiment to do because there are ethical problems or whatnot. Like, you would not want to release a potentially harmful organism in the environment wondering how it would spread before you know how it could, right? So you want to be careful with many things. And so that's another place where mathematics can be really helpful. It depends on the level of complexity that you want to work on, what it can help in biology.
Okay. Well, first of all, that was a very good answer, I gotta say. But moving on, so what are some of the current big problems in your field? What's the Riemann hypothesis of mathematical biology?
That's actually interesting. I was thinking about that because I don't know if mathematical biology has something like a Riemann hypothesis or Fermat's theorem or Poincaré conjecture. And I certainly don't think that they have that on the mathematical end. There could be an ecological or biological question that biologists find really interesting, like a question of the century or something. But I don't know if there's a particular mathematical holy grail.
Okay.
I think everybody who works in this area is working towards the goal of making models that are amenable to analysis, linking them to data to have an actual impact, and doing all of this in a way that is consistent and that gives actually new insight. And I think finding the right level of model complexity for each and every single problem that one looks at, that's a bit of the holy grail there.
Okay.
And that can change from model to model.
Yeah, so you would say then that all of the individual problems, figuring out the best fit model for that is kind of like the open problems in your field. It's like, what's the best fit for this model or for this real life situation?
Yes, I think so. And then it depends. I'm working very much on the mathematical side, but for people I think who work a lot more on the data side, one of the questions certainly is, how do you integrate? How do you deal with massive amounts of data that come out of experiments and observations these days, automated observations often? How do you deal with them in a way that really gives you new insights? That is certainly a problem that many people face. I don't, because I don't work with data, but many people in the field certainly work on that.
Okay. So then another question: you work primarily with differential equations, right? Like that's your biggest.
Let's say dynamical systems. Yes.
Sure, dynamical systems. Okay.
Yeah.
So what would be the difference in what you study and like a pure mathematician who would be studying dynamical systems? Because I just came out of a chaos and fractals course last term, so that was my introduction to dynamical systems. But what's the difference when you apply it versus whenever you're just researching it? Like, do you guys use the same tools, or?
We use a lot of the same tools, yes. So when I write down a model for something for the first time, then I do the usual checks. Is the model well posed? Do we have existence and uniqueness of solutions? That is very mathematical, and that shows my training, of course, which was actually in pure mathematics and not in applied mathematics. And then I move on to more qualitative analysis, where I look at, in the simplest case, what are steady states of the model? Are they stable? Are they unstable? And then after that, we're going to more complicated behavior. I think well, there's both. So sometimes I come up with models that pose new analytical challenges. Like a while ago, we came up with a model of a set of partial differential equations where we first had to show the existence of solutions because it was not covered by the classically available theorems. So it's very much a very nice applied mathematics, almost pure mathematics question. But then, on the other hand, I have a different goal often. My goal is to answer a scientific question. And so when certain things are covered, like the existence of solutions and some basic stability questions are covered, often the thing that I want to answer may not be easily available in terms of a mathematical answer, or may not be something to prove. So then I can use numerical simulations and explore. Once I've made sure that my model is reasonable, I can explore how it behaves. And I can do that numerically and ask the specific questions that I want to ask. And that, I think, is then a level of applications that a pure mathematician would typically not go to.
Okay, fair enough. So when did you decide that mathematics was the career path you wanted to follow?
That is also an interesting question. So, when I finished high school, I knew that I liked math a lot, but I also liked a lot of other things. And to me, it felt like focusing on mathematics was narrowing me down way too much. And I was actually afraid of choosing any one particular subject for university. I did not want to limit the breadth of subject areas that I had so much enjoyed in high school. What really helped me at the time was one conversation I had with somebody who was very experienced as a recruiter for many companies. And that person told me, it doesn't matter so much what you do now in your studies. What really matters is that you really enjoy doing it, that you're good at it, and that you keep your eyes open left and right. And so, just because of that, but to some extent because of that, I decided, okay, I'm going to do mathematics because I'm pretty sure I will enjoy it. And what happened after that was, after the first semester, I was hooked. I discovered that mathematics was by no means limiting. It was much more like opening many, many new worlds that I hadn't even known existed. So in that sense, that question never came up again. So I knew that mathematics was for me after the first semester. But then, so I studied in Germany. I went to a diploma, which is something like a master's with a thesis. And after that, it was not at all clear to me that I would want to stay in academia. I looked around. I even looked at a job or two, and they were just not interesting enough to me. And then I met a professor who would become my PhD supervisor, and he was somebody who could really motivate me and inspire me, and so I went with that. And then again, after the end of the PhD, it wasn't clear that I would stay in academia, because in Germany the system is slightly different. There are many jobs outside of academia for which a PhD is helpful or even required. And so again, I was looking around, but then there was this announcement of a postdoctoral position opening at the University of Alberta in mathematical ecology, where I could combine my experience and knowledge in mathematics with my interest in ecological questions, and I was hooked. And so after the first year there, it was clear that this is what I wanted to do. But it wasn't straight from the beginning.
Fair enough. Well, you found your way.
I did.
Well, what about mathematical biology did you find so appealing? And when did you take, because I don't imagine during your undergrad they had very many mathematical biology courses.
I didn't take a single math biology course. Well, I took one that was called Population Dynamics on the graduate level.
Okay.
But that was the only one, really. It just wasn't a big field at the time. My PhD supervisor was one of the founders of the Journal of Mathematical Biology, so he had some experience in that, but he was one of the few at the time. What I found really appealing about mathematical biology is that interplay between insights and observations in the real world and insights and results in mathematics. And so I could have a biological system and model that and find out what the model does and realize that the model doesn't do what I think it should do, and realize that my model was wrong. So I could tell from the mathematical analysis that I had missed something. I also really appreciate and enjoy that I can talk to people about what I'm actually doing at work. Because when I tried to talk about my master's thesis, which was in several complex variables, I could not talk to anybody about that.
Mm-hmm.
So I really like that. I really, after I've come to mathematical biology, I also really appreciated the community there. It seems that all the people I've met in mathematical biology are just really nice, helpful, cooperative people, collaborative people. It's a very nice community.
Nice. That's great. Yeah, that's what I love about the math people. Math people are always so nice. But yeah, it's funny that you mentioned that you weren't able to talk to anybody about your complex variables. I hear it only gets worse. I interviewed another prof at Waterloo, Dr. Brian Forrest. He's in amenability theory, which I have no idea what that means, even after talking to him for an hour. But apparently there's like only a couple dozen people in the world that have done that are in this subfield. So
I can imagine.
Yeah, it's the farther you go, I guess, the less and less people you can talk to, at least
Yes.
in pure math. But you did mention that originally your training was in pure math.
Yes.
So what made you decide to switch? Was it just the fact that you didn't really have anybody to talk to about your research, or?
Well, it was where I got my inspiration from. And my master's thesis is in pure math, Then, but just before I finished that, I had this course in population dynamics with Professor Hadler, and he could really inspire me. He made me see a lot more than just the equations and just the techniques. And then after that, it was my postdoc supervisor, Mark Lewis at University of Alberta, who could really inspire me, who had these great visions about how mathematics and biology should interact and should get together. And so I always went, or often went, the direction where I found inspiration.
Yeah, well, that's a good way to do it, I think.
I think it's the only way to do it.
Yeah.
Because I have to be really inspired and I have to really want to do the work that I'm doing. It's too much time and too much effort to do it if you don't really like what you're doing.
Okay, yeah, that's true. Now here's a silly question for you. Does studying mathematical biology change the way you see the world in a sense? Like, for example, talking about how groups of animals move, I was thinking about, I saw a video where they were studying how people move through like the main subway station in New York.
Yeah.
And they're like, look at all these cool math things. So does it change the way you see the world?
Absolutely. Yes, it does. And I would love to quote a piece by Richard Feynman, but I don't think I can still remember all the details. But it's in his book, Surely You're Joking, Mr. Feynman. And he describes, maybe even in the introduction, how he had a friend who said, oh, you physicists, you only see the world through the physics eyes and you don't see the beauty of the world. And Feynman replied, not at all. We see the beauty of the world and we see all the physics behind it, which is yet another dimension of beauty. And so he claimed that by his training as a physicist, it was actually more beauty that he could see. And I see something similar in math and math biology, that I read something, I hear something, I talk to people, I get into talks at conferences, and then these things pop up in my life in other places, on the radio or when I go travel, and I see them, and I see so much more just by knowing what can be there. I find it enriching.
Yeah, for sure. But I mean, at some level, it's got to be a little unnerving too if all these equations and that can model people's behavior. There's a philosophical question for you. Do the existence of these mathematical models that can accurately predict how people will behave in groups bring into the question whether or not we've got free will or something? Do you think? Do you ever think about that? It's not really a mathematical question.
It isn't a mathematical question, but I think the way you asked it allows for a partial mathematical answer, and that is, when we are able to model things like how a large group of individuals behave, then that's exactly what it is. We cannot predict what the individual does, but we can predict the ensemble. So in some sense, that's like a central limit theorem, right?
Okay, yeah, hey, that's a really cool connection.
you can't tell about the individual particle, but if you have a large enough number, then you can say what the average does. And I think that doesn't exclude free will, but I do not want to go in a discussion of free will. I don't know enough about it.
Yeah, fair enough. I just came off the top of my head. Well, let's go back to kind of like your university experience. What was your favorite course you took, probably in your undergraduate? Just it's most of our audience, so.
Okay, so I think there were probably two. There was what was called Algebra 2 at the time, and that was, oh my, I'm missing the word.
Our Algebra 2, I think, is linear algebra.
No, it wasn't linear algebra. That's not what I meant.
Oh, okay.
I'm sorry, I'm drawing a blank. I can provide it later anyway.
Yeah, if it comes back to
I really liked the elegance of all of it. And the other one that I really liked was one on dynamical systems and celestial mechanics.
Oh, okay.
Where, in some sense, lots of questions about dynamical systems and differential equations were introduced and posed in where many of them originated, namely in the two-body problem and the three-body problem, between how the sun, the earth, and the moon would move. And so that I also found very interesting.
Yeah, that sounds like a cool course. In hindsight, what do you think the most important class any undergraduate math student will take? And I'm sure that varies depending on which field you go into, but is there one in particular that you think is important for every math major to have?
It may sound really funny, but I think the two things that really everybody needs to be really, really good at is they need to do what we teach here on the third year analysis level, and they need to have an equivalent class in linear algebra, because these two courses just teach concepts that are ubiquitous and permeating everything in mathematics.
Mm-hmm.
You can't do mathematics really, I think, if you don't really know good analysis and good linear algebra.
Yeah, well, linear algebra is ridiculously powerful.
Yes.
It's so surprising everything you can do with linear algebra.
Exactly.
Yeah. What was the first mathematical result you remember producing, even if it wasn't like publishable?
Yes. So I remember that I was sweating over my master's thesis classifying so-called real Cartan factors. And at the time I was really proud, and I think it was an original result, but I also think that my master's supervisor knew exactly what the answer would be. In particular, now that I have seen how master's theses work from the other side of the table, I'm pretty sure he knew what the answers would be. So yes, it was original, but oh well.
Did you ever do any kind of like mathematical side projects on your own outside of like the school curriculum or outside of your theses?
No, I was always too much interested in other things.
Oh, okay.
I was happy to do all the math that needed to be done, and I was happy to read a little bit of extra here and there, but I also always wanted to have time for the other things that are important in my life.
Yeah, fair enough. You gotta have that work-life balance. And well, what would you say is your proudest mathematical achievement?
So there's one paper that came out in SciAm Reviews that I'm quite proud of. That work originated in my postdoctoral work, and it's also, I think, the result that was instrumental in getting me this job.
Oh.
Because it was fairly new by the time I got to my job interviews, and I think people were really happy and impressed to see that some very clear and concrete biological questions could lead to some really interesting mathematical problems that would warrant for fairly big and somewhat insightful proofs. More recently, there has been a piece of work that I did with a graduate student of mine, and this came out in 2013, but we're still feeling the effects of it, and it's almost as if it has started, I don't want to say a subfield, but maybe a subfield of a subfield, where it turns out that it's so much richer than I thought it could be at the beginning. So I'm kind of proud of that.
Yeah, well, if you make a whole subfield, that's something to be proud of. Well, what's the process of creating a subfield like?
Well, so this was one of those things that was driven by a biological question that's very easy to explain. We were interested in how individuals move through a landscape that consists of very, very different types of habitat. And the motivation came from observations in the Brazilian rainforest, where there's clear cutting going on. And the question is, how do songbirds react to that? Songbirds clearly like and prefer the original existing rainforest over the open areas. But sometimes, in particular, if these remaining patches get small, they have to cross and, take a plunge and go fly somewhere else and find other habitat. And so we wanted to know how we can put something like this into, again, equations for movement, differential equations, partial differential equations. And we found some previous work that people had done that we could build on, and we managed to come up with sets of equations that were somewhat new. At least some parts of it were new. And very quickly it was clear that these equations did something right that other equations hadn't done right before. So right in the sense that they gave results that qualitatively matched observations. But that was only the beginning. Then comes the whole question of, do solutions exist? Are they unique? How regular are they? And all of this. And we're still working on that. Not all of that is known.
Wow. That's pretty cool. So, well, the flip side to what your proudest mathematical achievement is what's the one problem you wish you could solve but haven't been able to yet?
Well, maybe work-life balance. But I'm sure you're talking about a mathematical problem. So as I said before, mathematical biology doesn't have like its Riemann hypothesis or its Poincaré conjecture. So in that sense, I can't really answer that question. The one problem that I haven't solved and want to solve, I wish I could solve, is always the next one that's on my to-do list. There is actually one right now that has to do with the songbirds and the models that came out of that. And that is, so in very simple models for biological invasions, there is something that's called a traveling wave, which is a solution that moves across at a constant speed and that we can interpret as a biological invasion, as a biological organism that's spreading in space. And so what I haven't been able to show yet is that the similar kind of solution exists for these kind of equations that we introduced a bunch of years ago.
Okay. Yeah. Well, some of the other mathematicians I've interviewed, I've heard a couple of times now that there's like two camps of mathematicians. There's those that kind of, bunker down for a decade and just work on like one problem, and then there's others that kind of spread their wings and they jump from problem to problem to problem. And I find that mathematicians who kind of just jump from problem to problem to problem tend not to have an answer to that question. Or it's like, well, it's whatever problem I'm working on is the one that keeps me up at night.
I confirm that rule.
Yeah. So it's just interesting because it's I think you're the third person with that answer that we've interviewed. Okay. Well, my next kind of sub question to that one. So even if it's just whatever problem you're working on now, what kinds of things do you try whenever you get stumped? Like, do you have some fallback things that you always try and try, or is every problem just so much different than the last that you can't really rely on anything you've tried before?
So that's another thing I like about applied mathematics and mathematical biology. If I get stumped on something, I can always go to the computer and, if nothing else, simulate and look at it long enough and hopefully get some insights and ideas that way. Sometimes that works. I go to the literature and look, and I go and talk to colleagues. As I said earlier, the whole math bio community is very collaborative and very friendly. So I talk to people and they point me to the literature. Because one of the things that is really typical for applied math is that you're never done with your toolbox. There's always another tool that you can learn somewhere, and there will always be a problem for which the tools that you have are not sufficient, and then you need to learn another tool. And so, yeah. Sometimes I even give up, but that doesn't happen very often.
Well, that's good. That's good to hear. And actually, I do remember that problem that I was going to ask you earlier. Okay, so you were mentioning at the very beginning, the songbird problem is one that's really simple to explain. And so in that sense, I want to ask you a question, because I've talked to a lot of number theorists, and the thing about number theory is all the problems are really easy to explain. Like, if you know what a prime number is, you could explain it to a fifth grader. And they'd at least have some understanding of what it is you're trying to do. The thing that goes along with that is that the easier the problems sound, the more people will kind of send like manuscripts to professors with saying, hey, I've solved the Riemann hypothesis, I've solved the Collatz conjecture. So I'm wondering, do you, as a mathematical biologist, get people sending you things saying, hey, I think I've solved this problem?
I have never received one for mathematical biology, but I have received one for Fermat's proof. Yes, for Fermat's theorem.
And well, how was it?
Oh, like page 3, things go awry, but it was interesting.
Well, I mean, you read all the way to page 3. That's pretty good. I know a lot of profs who just kind of throw those things out.
I was curious, and it's not my field, so I was.
Yeah.
But yes.
Do you have a favorite theorem?
I do, and it comes from number theory. It's one of the very first, in the fact that there are infinitely many primes.
It's classic.
And one of the reasons why I love that theorem is that, like you said, it's very easy to explain. In this case, even the proof is fairly easy to explain. And I think what it does is it shows people, it gives me a chance to show people who don't know much about math some of the power of math, and the fact that it can deal with infinity, which is probably the only subject area that can deal with infinity, that has basically evolved around questions about infinity. That's why I find it really cool.
So is your favorite proof of it the classical suppose that there are finitely many,
exactly,
that
yes,
many plus one,
the one that you can like you said explain to maybe not a fifth grader but shortly thereafter.
Yeah, exactly.
And that's my favorite.
There's I was actually interviewing Dr. Monica Nevins, I think on the floor above or next door.
Above, yes.
Yes. And we were talking about another proof of the fact that there are infinitely many prime numbers, which was really cool because we were talking about the p-adic numbers and how you get these discrete metrics. And so there's a similar thing that they do to prove that there's infinitely many prime numbers, where you take the integers and you define a topology on the integers by sequences, where open sets are convergent sequences or something like that. I'm not explaining it very well. But with that, you can somehow prove that there's infinitely many prime numbers, which I think is crazy. But math is...
and certainly not for a fifth grader.
Yeah, that one's definitely not for a fifth grader. But what I love about math people is that even if a problem is solved, they'll find a way to complicate it, recomplicate it, and solve it again in a harder way. There's the other one where because the zeta function at 3 is irrational or something like that, that means there's infinitely many primes or something like that. That's another one.
Or the fundamental theorem of not of calculus, the fundamental theorem of algebra that has that has
polynomials
many proofs, just not an algebraic one.
Oh,
something like
that. That's true. You need something from analysis to prove every single proof of the fundamental theorem of algebra, which is really funny. I think it's is it intermediate value theorem that you need?
Oh, I don't remember.
I think that's what the proof kind of hinges on. Yeah. Which is kind of funny that you can't have the fundamental theorem of algebra doesn't use algebra to prove it. Okay. Sub question about favorite theorem. I know that theorems are, depending on how applied your applied math is, theorems are somewhat less important than they are in pure math. So I'm wondering, in your work, how important are the actual theorems, or as opposed to how important are the methods?
So, for me, a project is really good if it's motivated by an interesting biology problem, if it creates interesting novel math, and if that math creates new biological insight. And so the middle step, where it creates new math, that's where the theorems are important. When I communicate these things back to the biologists, I usually don't talk much about the theorems. But that doesn't mean the theorems are not important.
Yeah, of course. Just your audience.
Yeah. So a really good project typically has 2 publications, one in a math journal and one in an ecology journal. And the one in the math journal certainly has theorems, and they're important.
Okay. Do you have any math jokes?
I do. A biomath joke, if I may.
Oh, perfect.
So, there's a biomathematician who goes for a hike and wanders along and stumbles across a shepherd who is out there with his herd. He looks over and says to the shepherd, "If I can tell you how many sheep you have in your herd, can I have one?" And the shepherd looks around and thinks, what a crazy guy, and says, "Sure, of course." And the mathematician says, "You have 297 sheep." The shepherd is absolutely flabbergasted and says, "Well, how did you figure that out?" "Well," says the biomathematician, "I counted the legs and divided by 4. And can I pick my sheep now?" And so he picks the sheep, and the shepherd holds him back and says, "Before you go, can I guess what your profession is, and if I guess right, do I get my sheep back?" Biomathematician says, "Sure, of course." Shepherd says, "You're a biomathematician. How did you figure that out?" "Well," says the shepherd, "you took my dog."
Oh, that's good.
So that's how far a biomathematician can think in terms of or recognize things outside in the real world.
That's too funny. That's good. That's a good one. Do you have any mathematical heroes?
I have never taken a class on history of math, nor have I taught one. So I don't have a whole lot to choose from. But Poincaré is certainly high up there for me. He single-handedly invented a lot of the modern views on dynamical systems and differential equations. And in general, I would say people have to somehow overturn their beliefs based on their own insights and new research achievements. I would say that always, I have a lot of respect for that.
Yeah. Okay. Well, if you do ever have some free time, math history, 10 out of 10 would recommend. You should look into teaching that course if you ever have something you want to teach. Because math history is just filled with lots of little nice stories from here or there.
I can totally believe that.
Yeah.
So last year I was in Munich for a while, and I went to the so-called Deutsches Museum, German museum, which has a lot of technical stuff and has a big mathematics section. And I was so in awe of all of these mechanical drawing devices where you can
really?
draw all kinds of curves mechanically. And one of them, the one that I found the best, was where you could draw a curve, a closed curve, and the device would mechanically tell you the area of the enclosed curve, enclosed by the curve. And so if I wanted to teach history of math, I would teach that.
That is so cool.
Yes.
What time period was it from?
I don't remember.
After or before 1900?
I want to say it was around that time.
Yeah, that's what I figured it would be around there. Because that was when the first mechanical calculators were coming out too, around then.
Yeah, but maybe it was even earlier. But yeah, they could basically mechanically integrate.
That's so cool.
Yes.
So
that's actually where I first said, I want to teach history of math once.
Yeah, well, you should, because then you could get a...
And then it would be a field trip to Munich, of course.
Yeah, you gotta. Well, if I'm ever out in those neck of the woods, definitely check it out.
Yeah.
Okay, so we're just about out of time. I've got one last question for you, and that is, what advice could you give to us aspiring mathematicians?
Well, I think I'm coming back to what I said about my career path. And that is go with the people and ideas that inspire you. And the other is do what you really want to do and be good at it. if you want to do mathematics, if this is kind of what keeps you up at night in a good way, and what gets you out of bed in the morning, let's say, then do it. Even if you think that maybe 5 years or 10 years down the road, you could make more money with some other degree, but if you don't like that other subject area, it's not going to work. You have to do what you really like to do. What gets you out of bed in the morning, that's probably a good subject to study.
Okay. Well, thank you very much for coming on the show.
Thank you very much for having me.